So thanks for having me today. We are, as you're undoubtedly aware, in the middle of a new industrial revolution that is fueled by insights derived from data. Data is the object of computing. And to get to insights, you need two things. You need the data, and you need algorithms that process the data and turn it into valuable information. Today I want to talk to you guys about algorithms whose object is not data, but other algorithms. Today I'm going to talk to you about algorithms that make other algorithms better. So an algorithm can be a rather abstract beast, so I'd like to use a metaphor. Assume you have a car. There's lots of different things that you can change in your car. From the angle of your rear spoiler, to what gearbox you're putting in there with 4, 5, 6, 7 gears, to you can even replace the engine itself. In some sense it remains the same car, but it comes in very many different configurations. And no matter what you're after, whether you want a smooth ride or top speed, Autobahn, or say a fuel efficient car, the way how you configure your car is going to greatly affect the performance. Now you have all built algorithms, from predictive models to logic reasoning technology to making sense of audiovisual data. And you know that your algorithms have parameters. They have these little knobs that you can turn, from little thresholds to the decision what kind of subroutines are going to get invoked during the computation. And the way how you configure your algorithm is going to greatly affect the performance, very much like in this metaphor with a car. Now the complication arises from the fact that the car manufacturer doesn't know what the user is going to ride the car on. Nor do you as an algorithm developer know what inputs your algorithm is going to face later on. So what you would like to do is you would like to find a configuration that is going to work robustly across the board, across very many different kinds of inputs. Right? You want to choose one configuration that's going to work well on all of these different tracks that you see here. Now algorithms are a tad bit more powerful than cars. They can actually self-adapt. So what you could do is you could actually, for an algorithm, it could actually choose its own configuration at runtime. It can look at, oh, this is my input, this is the configuration I'm going to use. So either think of a transformer car that looks at the racetrack and transforms, or say you're a very rich guy and you have very many different cars in very many different configurations. What you want to do is you want to pick the right car for the right racetrack. Right? This is what we're trying to do. So why does this matter? Well, number one, performance. There are, in the literature you will find experiments that were done where developers of algorithms were asked to tune their own algorithm, which they knew better than nobody else, on a given set of instances. And afterwards we gave it to a computer to configure this algorithm. The computer did 3 orders of magnitude better than the developer of the algorithm. The second reason why you want automatic tuning tools is the very fact that it's inconvenient to have to get a human into the position to tune the algorithms, because you have to somehow communicate what these parameters are doing. You have to write a book, you have to write a user manual. It's not something you want to do. The third aspect regards research. Often we have multiple approaches that we could use for the same task, and we would like to know what is the right approach. But when you do experiments with a computer, what you're really comparing is concrete configurations of each approach. And in order to really see what the potential of the approaches is, you want to level the playing field. You want to tune them equally well. So if you had an automatic tuning tool, you can much more effectively make sure that the tuning levels are the same. The last aspect that is on this slide is really the most important one. And that is the fact that you can exploit experts. You can have approaches that really don't work robust at all. They just work on a narrow slice of inputs, but here with stellar performance. You never use these ideas because across the board this doesn't deliver good performance. If you have an automatic tuning tool and the self-adapting capability, now at runtime you can choose the method that is, this is its day to shine and you're picking it out of there. So it changes the paradigm on how you're programming and how you're actually achieving stellar performance. Okay, so now imagine that we are in this space. We have lots and lots of different configurations that we can try. and we have a given set of instances, inputs that we want to try our algorithm on and configure it for. Now what you can do is you can try them out. You can emulate what a human is doing. You pick a configuration, you run it, and you say, oh, this wasn't so great. Let's tweak this parameter over here. This is called a local search. We transformed this local search into a population-based local search. So we used a genetic algorithm in order to do this kind of search. So we have, at any given point in time, very many different configurations in what we call a gene pool. And what happens in a genetic algorithm is that individuals are selected, they mate, they get new offspring, and that is getting evaluated, and it's, you know, depending on your fitness, you're going to have either more offspring or you're going to die earlier. Right, that's essentially how it goes. And so over the course of many generations, you're seeing an improvement of the configurations that you have in your gene pool. Now the problem that I have here is that compared to where normally genetic algorithms are being applied, it is an extremely costly to evaluate objective function that I'm dealing with. I'm taking my parameterization, I configure my algorithm, I run it on all the instances. It takes seconds, if not minutes, if not half an hour or an hour, for one evaluation. So this causes two problems, which unfortunately aggravate one another. First one is I can't have very many individuals in my population because I would have to evaluate them all. And that means I'm going to have very limited diversity in my gene pool. It's not good because you might not be finding an optimal solution, but you might very quickly get stuck in a local optimum if you can't really traverse the entire space. The second one is you also can't have very, very many generations. And the problem there is that if you don't have very many generations, you need to be very aggressive in making progress. You need to find good configurations very, very early on. And of course, if you do that, if you're very aggressive in your selection, you're going to lose even more diversity. So this aggravates one another, and this happened before. It happened in nature when it went from one-cell organisms to something like deer. And on a genetic level, we were wondering, well, what actually changed when going from bacteria to mammals? Do you have an idea what on a genetic level the main difference between bacteria and mammals might be? Not really. Well, actually, the answer is staring you in the face. It's genders. Actually, there's another one, and so it's the existence of chromosomes itself, which kind of gives you the ability to recombine different ideas without ending up with a recombination that necessarily, or most of the time, results in something that isn't livable. But the very fact that we have genetic reproduction gave us an idea. So we're not claiming here that this is why nature has genders, but it gave us an idea because we had two genders that we're familiar with, and we had two problems. One, the diversity, and the other one, making rapid progress with respect to optimization. So what we did is we said, let's split the population in two halves. One of them is going to be non-competitive. This is my diversity store. This kind of gives me lots and lots of different genetic configurations that I can choose from. And the other side is competitive. These guys, in order to mate, they have to go to the clearing and fight for it, right? Just like deer do every fall. And there we are very, very aggressive. I mean, it's aggressive to a point where a normal genetic algorithm would just break down and move into a local minimum immediately. 1 in 10 guys wins the right of mating, and the other ones just don't. And then there's a certain age restriction in order to keep the population in check. So after 3 or 5 years or so, they die. So you get another chance next fall if you're competitive. But if you just never make it, if you never win your tournament, you will never get to procreate, and your genome dies with you. Okay, so now you might wonder, and this is a question that I get a lot, is, well, does the non-competitive side of the population somehow trail in performance behind the competitive one? And it's a very intuitive thing to think, but actually this is not the case. So what you're seeing on this slide here is the average performance in the population as well as the peak performance of the population, with the black curve being the non-competitive side of the population and the lighter curve, the gray curve, being the competitive side. And you're seeing that really there is no difference. They sometimes overtake one another, and this is just one example, and sometimes we see one population being on top of the other. Now, if you think about it, this really shouldn't be that surprising after all, because the offspring is generated from a competitive and a non-competitive parent, and then we flip a coin on whether you're going to be non-competitive or competitive. So your performance should really depend on what you're inheriting from your parents rather than how randomly your gender was selected. Right? So you're actually not seeing that. Okay, now, if I'm talking about configuring general algorithms, you know that there are different kinds of parameters that they can have. There can be categorical parameters in the algorithm, so something like which engine do I put in my car, right? So which subroutine am I going to use? Am I going to use a k-nearest neighbor support vector machine, right? And you can choose which one you're actually going to use. You can have ordinal parameters, so think of the number of gears that I gave you before. You know, six-gear gearbox is closer to a 7-gear gearbox than a 4-gear gearbox. Right? So it's kind of you also have a discrete relationship between these values that this parameter can take, but there is an ordering to it, which is not there in the categorical parameters. And then finally, you can have these thresholds, numerical parameters that can take any value, which of course really make your parameter space explode, because now you have a continuum, you have an infinite number of configurations you would have to choose from. So we group them in these variable trees, and now in order to generate offspring in its first incarnation of this algorithm, what we did is we chose a non-competitive parent, we chose a competitive parent, and then we did a form of a mutation crossover in order to generate new offspring. That worked reasonably well. Actually, it still works better than any other algorithm tuner that is out there, but recently we've had a new idea, and this is really what I want to talk to you guys today. Namely, if it is that expensive to evaluate a new configuration on my algorithm, could I try to forecast where I might actually find good configurations in the future? So what we do is we take the experience, whenever we evaluate somebody, we take that experience, how well was that, was the result of that configuration. And now we train a predictive model. We call that a surrogate. And we're going to use this surrogate in order to forecast where we might find even better performing individuals. So this is the idea. You predict the performance using a non-parametric model. Using a non-parametric model is very, very important. You want a low bias machine learning method here. You do not want to assume that, say, the algorithm performance was somewhat linear in the parameters that are going in, just because it's wrong. It's an assumption that doesn't hold very often. So you want something that's non-parametric and that can refine based on your experience as much as it wants. Now the question is, how do you actually get that into a genetic algorithm? How could you use such a surrogate model in a genetic algorithm? And what we did is we said, rather than taking this random mutation crossover that we had before, could we choose the parents and now build the best possible offspring that these two can have? We engineer offspring, and we choose the offspring that is going to be generated based on the prediction that comes out of the predictive model. So that was the idea. Now the question is, what kind of predictive model should you be using? I already said, well, let's use a non-parametric one. Let's look at one particular non-parametric model that you could be using. This would be a regression tree. Ultimately, we're going to use a random forest to do this, but a tree is kind of the basis for forest. So normally what you would do, so assume that you have two parameters, P1 and P2. The position of these points tells you what the parameters are for these configurations. And say the numbers that you find in there is the runtime of the algorithm. So lower is better. Okay? Now normally if I build a predictive model, I would like to build a predictive model that predicts everywhere equally well. Right? You don't discriminate the error that your predictive model makes based on whether this was an area where you find good parameterizations or whether this is an area where you find abysmal parameterizations. The thing tries to do equally well everywhere. So a typical way on how you would do this is you try to find a splitting point here. So to build this regression tree, you need to find a splitting point whereby in each of the two sides that you're splitting these number of points into, you try to get little variance if your estimate was the mean over the remaining items in each box, right? And then you recursively continue doing this, and in this case I forbade further splitting if I had less than 3 points in each box. And now ultimately I'm going to label everything with the mean in there, and this would be what my regression tree thinks I should be predicting, right? So if I'm, say, in the upper right quadrant over here, no matter where the point falls into, the tree would actually say you can expect runtime of 1.5. Okay? Now the point here is I'm really not interested in a good performance of this 9.8, the upper left quadrant that I have up there. Upper left box with 8.5. I could care less on whether this is a good estimate or not, because I want to know where the optima are. I want low runtime, so this is where I want to do well. So what we suggested is, how about if we actually split differently? We take the same framework for random forest and for a regression tree, but we're going to split slightly differently. Namely, we're going to split based on a criterion that tries to get me to the top, and you can choose the percentage, say the top 10% guys that you have in here. And you try to find a separation that actually works well. In this case, well, you a little bit have a conundrum because you have 2 1s and 2 2s, which are the 4 guys that this thing would actually focus on in the beginning. And there's really no way to get the 4 1s and the 4 2s on one side. But between the cut that you could have done horizontally to get a 1 2 and a 5, the 1 2 and the 4 was better because it's purer in its being optimal, right? So this is why it chooses this, and now you just recursively continue to do this kind of thing, and you see that you're going to end up with this, it kind of looks reasonable to a human just as much as the original one, but you kind of see that you have bigger boxes where you find optima, and you find that actually this one actually has a region that goes all the way to 1, whereas before I was stuck with a 1.5, right? So if you compare the 2 regression trees that you would get out of this to the left and the right, you see this here that the optimum is actually better and it's actually higher up in the tree. So it gives you a larger region in the parameter space where you think I might actually be finding good parameterizations here, which is important for our search algorithm to have. Okay, so long story short, we use that on top of our existing gender-based genetic algorithm. This is what GGA stands for, and compared it to our closest competitor with this SMAC, which interestingly enough also uses a surrogate model, but in a non-population-based local search approach. What we did with this is we went to the SAT domain. Never mind what that actually is. It's a very fast-paced area in AI around logic programming, solving verification problems with some applications also in cryptography. And we chose 2 of the best solvers that you can find in that area. There's glucose and there's lynchling. These 2 solvers have proven themselves in numerous competitions already as being stellar in performance. And they have very different characteristics. Glucose only has 8 parameters that you can tune. Some of them are continuous, so the configuration space is still very considerable. Lynchling has over 80. So, very different in say, your ability to configure these algorithms to do even better. So we were curious on whether we can. So if you look on the left-hand side, what are the criteria that we're using in order to decide which algorithm is doing better? Well, the typical thing that people do is they put a time limit. Because frankly, you have some solvers that solve an instance, a SAT instance, very quickly, and then you have others that don't come back for days, and you don't want to wait this long. So we've given everybody, for each instance, a threshold of 600 seconds, and we are checking on whether they can solve the instance within that time or not. Now, this sounds a little bit binary, right? You're saying, well, but shouldn't the one that solves everything in 50 seconds better be the one that solves everything in 599 seconds? And of course it should be. So people look at measures like park. So what does park do? For each instance that you solve, you actually take the actual runtime as the cost for solving this instance. For each instance that you do not solve, you take k times the timeout that you allowed, the time limit that was allowed. So if the timeout is 600 and you do a par 10, if you don't solve it, you pay 6,000 for that one instance that you don't do. This is a typical thing, and this was actually the objective for our tuner also to minimize. It's the same for GGA, for SMAC, and for GGA++. They all try to minimize this part 10 score. And now see what happens. On glucose, which only has 8 parameters, right? It's not a huge configuration space. You're going from the default of 350 part 10 down to 266. And this is a heavily tuned and beautiful solver for this particular case of instances, which are industrial instances. This is what it was built for. And now if you go to a solver like Lynchling, which has 80 parameters and you have way more room for improvement, you're going from 512 to 268. In fact, the number of solved instances grew from 85% to over 93%. So this is closing half of the gap to being perfect, right? Just by tuning this, not writing a new solver, you just take the solver and tune it and you do better. Okay, so with that, I would like to conclude with 4 important take-home messages. The first one is, do not tune your algorithms by hand, please. There are tools out there that can do this stuff for you, and they will do a much better job than you, even if you know the instances that you want this thing to solve. The second one is, if you want to understand what they're actually doing, genders and genetic engineering actually help you cope with expensive to evaluate objective functions. Now this transcends the application that we're talking about here, which is tuning algorithms. Whenever you have something that actually requires a long time to evaluate the objective function, these 2 ideas can greatly help you in order to get better performance out of a local search algorithm. The surrogate models, if you design them, don't take a machine learning algorithm just off the shelf. Think about what it was designed for to do, this predictive model, and then think whether that supports your application or not. In our case, it didn't, because the algorithms that build these predictive models were built to do a good job everywhere. And I don't care about everywhere, I care about peak performance, so I want to do well there. And the last thing, to me the most important one, is this paradigm shift that we're observing here. Using this technology, suddenly these ideas where you thought, oh, this should be great, and then you find, yeah, and it is great, but only for 2 out of 100 inputs that I could be facing. So overall, I need to discard it afterwards. Suddenly, you have a technology at hand that allows you to make use of these ideas and to give them their day of shining, because you have something that actually chooses them on the fly. So with that, I conclude, and I have to thank my co-authors for this work, Carlos Anzotegui, Jure Malitsky, Horst Simulowicz, and Kevin Tenney.